In this video, we revisit this initial value problem. We solved it in the last video. We had y double prime equals x plus sine of x, and we were told that y at 0 is equal to 5 and y prime at 0 is equal to 3. I wanted to solve this with you on desmos.com so that we could see how that function changes as the values of the arbitrary constants C1 and C2 change, and how these two conditions are satisfied by choosing the right values of the constants C1 and C2. So let's do that. We'll look at the solution on Desmos. Okay, so we had this differential equation. It was second order. And we had these two initial conditions. In order to find y, we antidifferentiated twice. So when we take the antiderivative of y double prime, the antiderivative of x is that 1/2 x squared. The antiderivative of sine of x is the negative cosine of x. Then we add that constant of integration. And then when we antidifferentiate again, we antidifferentiate this term, which gives us 1/2 times 1/3 x to the third, which simplifies to 1/6 x to the third. And then we subtract the antiderivative of cosine of x, which is sine of x. And then we add the antiderivative of C1, which is C2 times x. C1 times x, and then we add a second constant of integration. So our solution looks like this. It's sort of a cubic polynomial where the constant multiplying x is to be determined, and that constant term on the very end is to be determined. The value of C2 just shifts the graph up and down. So as we change C2, we have the exact same curve. The slope doesn't change, but we shift it up and down. Now, as we change C1, that does actually change the derivative. So it changes the shape of the graph. And because it changes the shape of the graph, we're going to have a different slope. Because whenever we take the derivative of this C1 times x, we get a C1. So these are our solutions. This is our infinite family of solutions. For every value of C1 and C2, we have a different solution. C1 just moves the graph up and down, and then C2 moves the graph up and down, and C1 changes that shape of the curve by changing the coefficient on the x. But that is our solution. Now we want the particular member of that family of solutions that satisfies y of 0 equals 5 and y prime of 0 equals 3. So in order to find that, we computed y prime, and we had actually already had that from a previous step. We have y prime, or dy dx, equals 1/2 x squared times cosine or minus cosine of x plus C1. And we can evaluate that at x equals 0 and set it equal to 3. That gives us an equation for C1. And we can also evaluate the solution at x equals 0. When x equals 0, we get 1/6 times 0 cubed, which is 0, minus sine of 0, which is 0, plus C1 times 0, plus C2. And that has to equal 5. So we find out that when we substitute 0 for x in the solution, that C2 has to equal 5. So we do that calculation. We did that on paper, and we got 5 for our C2. And then we said, when we evaluate the derivative at 0, we have to get 3. Well, the derivative is 1/2 of 0 squared minus cosine of 0 plus C1 when x equals 0. So we end up with a -1 plus C1 has to equal 3. So then C1 has to be 3 plus that 1. So C1 has to be 4. So we end up with C1 equals 4. And that is the particular member of the family that has the right shape. It gives us the sort of right curve for our function. Oops. I don't like that. I don't like it in the grid because it's like the grid lines are too bold. But I did want to show you, oops, sorry about that. I did want to show you that this is the particular member of the family that satisfies both initial conditions and has this form. So we know that C1 equals 4 and C2 equals 5, and that's our solution. Now, if we want to, we can see that the function satisfies those initial conditions by graphing the points. So we can plug in x equals 0 to the solution. And we've already got the C1 and C2 selected by choosing the right value on our sliders here. So we can see that when x equals 0, y equals 5, which is what was supposed to happen. Now we also wanted y prime to equal 3 at 0. And when we substitute x equals 0 into y prime, we get that answer equal to 3. But we can visualize that graphically by graphing the linearization. So the linearization is just our tangent line. I want my tangent line at x equals 0. So that's equal to the solution at x equals 0 plus the derivative of the solution times x. So I've got my tangent line here. And if I plot another point on that tangent line, I've got that right there. Actually, I think I may have made a mistake. Is that right? Yeah, C1 equals 4, C2 equals 5. That's correct. Now the claim is that the slope of that tangent line is supposed to be 3, and it is. The change in y, as y goes from 5 to 11 is 6, and then we're dividing by 2. So change in y divided by change in x is 6 divided by 2, which is 3. So we've got the correct slope. We can also see it from right here that we have the correct slope. So we have chosen a member of the family that has the appropriate slope and that has the appropriate function value and also satisfies the original differential equation. So if we differentiate twice, that derivative, that second derivative will be given by this x plus sine of x. And we can see that if we type it. So let's actually type that. We know that the solution equals this. I think I'm just going to type it, replacing C1 and C2 with 4 and 5 respectively. I'm going to call that PS now for a particular solution. And C1 was 4 and C2 is 5. So it's the same graph as before. Now the derivative of that is 1/2 x squared. Oops, that x squared should be in the numerator. Minus cosine of x plus 4. So if I want to, I can graph that function on here as well. Can't see it for some reason. I'm just going to call it PS prime actually. And so we have that function. And then if I take the second derivative of that, y sub PS double prime, I have the derivative of 1/2 x squared is just x. And the derivative of cosine is, or negative cosine is positive sine. And so our derivative is right. We got that x plus sine of x. And then when we take the antiderivative of that, and we require that antiderivative the antiderivative of y double prime being y prime, we require that derivative to have a value of 3 at the origin. I'm going to plug in 0 there. You see my y value is 3. So let's graph that ordered pair now. So our second derivative is that orange graph. And our first derivative is this teal graph. I have that tangent line there as well. I don't really need that right now. And we've got the original function. When x is 0, y is 5. And the first derivative, when x is 0, y is 3. There's a lot of kind of cool hills and valleys. And that's because we're taking that x and we're adding sine of x, which oscillates between -1 and 1. So we got this like some kind of neat second derivative curve. But none of that is necessary to solve the differential equation. You just anti-differentiate twice, evaluate the original or the solution and the derivative at x equals 0, substitute or set those values equal to 5 and 3 respectively. Solve for C1 and C2, and then substitute those into the general solution to get a particular solution. In this case, our particular solution is that one right there. And if we graph the tangent line and a point on the tangent line, we can see that not only does the original solution pass through 5, it has the right slope, or when x equals 0, the y value is 5. It has the right slope at x equals 0. And it has a slope of 3, which is what we wanted.